In the previous video, we saw the Taylor series or the Maclaurin series expansion of sin x. Now, using that, let's say I want to find the Taylor series centered at pi over 3. Now, to do that, I need to recall that what's going to happen is, in that case, f of x becomes f of a plus f prime at a, not 0, right? X minus a over 1 factorial f double prime of a x minus a squared over 2 factorial f triple prime of a x minus a cube 3 factorial, so on. So let's do that first. F of x is sine x and f of pi over 3 is sine pi over 3, which is root 2 over 2. F prime x is cosine x. F prime cosine of pi over 3 is 1/2. Second derivative is negative sine x. So f double prime of pi over 3 is negative root 3 over 2. And then f 3 triple prime is negative cosine x. We know it repeats after this, so I can stop at triple prime. This is going to be negative 1/2. So what I have, f of a is root 3 over 2 plus 1 over 2 times 1 factorial x minus pi over 3. Then you have a minus root 3 over 2, 1 over 2 factorial x minus pi over 3 squared. And then you again have a minus 1 over 2, 1 over 3 factorial x minus pi over 3 cubed. The pattern here is positive, positive, negative, negative. And then the next term is going to be positive, and it's going to be back to root 3 over 2, but a 4 factorial and a power of 4, and so on. Binomial series is again a very useful, famous series that we want to study. Finding the general formula for 1 plus x to the power k. So let's use Maclaurin series here. F of 0 is 1. F prime x is k times 1 plus x to the k minus 1. So f prime 0 is k. The second derivative, then I get k times k minus 1, 1 plus x to the k minus 2. At 0, that's k times k minus 1. Third derivative is k minus 1, k minus 2, 1 plus x, k minus 3. So the third derivative at 0 is k minus 1, k minus 2. So you see the pattern of what's going on. Eventually, the nth derivative will be such that the nth derivative at 0 is k factorial. Is k minus 2, k minus n plus 1. So what's the Maclaurin series? So the Maclaurin series becomes f of 0, which is 1, plus f prime, which is k x over 1 factorial, k minus 1, x squared over 2 factorial, k minus 1, k minus 2, x cubed over 3 factorial, plus so on and so forth. These numbers have a special name. These numbers are called binomial coefficients. And there is a simpler representation of them written as kn. which is given as k factorial n factorial k minus n factorial, which is essentially what you have here, because you have a factorial term, and k times k minus 1 means it can be represented. For example, 7 times 6 can be represented as 7 factorial over 5 factorial. So what you have is, you have this general result that 1 plus x to the power k can be written as sum of binomial coefficients x to the power n, which is 1 plus kx plus k minus 1 over 2x squared plus k minus 1, k minus 2, 3 factorial x cubed, and so on. Another example, evaluate this as an infinite series. This again becomes a useful sort of application, because you know that e to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. This means e to the negative x squared would be 1 minus x squared plus x to the 4 over 2 factorial minus x to the 6 over 3 factorial plus x to the 8 over 4 factorial, and so on. So if I were to integrate this, it would be the integration of this entire sum, which would come out to x minus x cubed over 3 plus x to the 5 over 2 factorial times 5 minus x to the 7 over 3 factorial times 7, etc. Which means even if I'm not able to find the actual antiderivative, I can find it as a series. Another application is evaluation of limits. Now this particular limit by L'Hopital's rule is e to the x minus 1 over 2x, and you apply it again, e to the x over 2, so it comes out to 1/2. Another way to apply this is to use the expansion for e to the x, and it's this infinite series, and from this infinite series you take out these two terms, which means these cancel out, and you divide by x squared. Now everything, if I factor out an x squared on the top, I have 1 over 2 factorial. These have x, right? So under the limit, as x goes to 0, all of these go to 0, and I'm left with 1/2. This is another neat application of Maclaurin series, or series representation of functions. The last topic will be in the next video, which is a brief application of Taylor polynomial.